Let us see the recursive C++ implementation. In this recursive implementation, I am considering this node where we have key, left and right pointers. We have a constructor which initializes the key with given value and initializes left and right as null. Let's see the recursive code for searching. So one is base case. If somebody passes an empty root, then we should return false, that the key is not present. Whatever key you are passing, it cannot be present in an empty root. This is also important to handle the base cases, because when you are searching for a key and if the key is not present in the tree, you end up with a null. For example, if you search for something like 19 here, you will come here, then you will come here, then you will come here, which is a null. Right of 18 is null. So for handling the empty tree and for handling the base cases when the key is not present, for both the things we need to have this condition. If root is null, then return false. Now we check if root itself matches with the given searched value x. If root itself matches, then we return true. For example, if you're searching like 15, right? This is again important not only for root, for other nodes also. Because when you come to 20, you will be recursively calling for 20 and this will be your new root, right? If root arrow key is greater than x, if the key that you are searching is smaller than root, then it can only be present on the left side of the root. So we recursively call for the left side. And if it is greater, then you call for the right side. And you simply return whatever these calls return. And these calls are going to end up either here or here. If they find the key somewhere, they'll return true. If they reach a leaf and if they reach left or right of a leaf, which is a null, then they will return false. Let us now talk about iterative implementation. In iterative implementation, we take a pointer, we begin this pointer as root, we compare root's key with the searched value x. If they match, we return true. Otherwise, we change this root pointer to root arrow left or root arrow right according to the comparison result. If the searched value x is greater than root, then we do root equal to root arrow right. If it is smaller, then we do root equal to root arrow left. So this is the iterative code here. We run a loop while root is not equal to null. If root becomes null at any point, that means key is not present. The value that you are searching is not present at all. And you come out of the loop and you return false. Even if your initial tree is empty, you will not go inside the loop and you will return false. So you run this loop. At every instance in this loop, you compare root's key with the searched value x. If they match, then you return true. If the root's key is smaller, then you need to go to the right side. For example, if you're searching like 25 here, then you go to the right side. If it's greater, then you need to go to the left side. That's the simple iterative implementation. We have talked about recursive and iterative implementations of BST search. Now, what is the time complexity of these operations and how much auxiliary space they require? So if you look at this search function, it goes across the height. Suppose you are searching for 16, you will come here, then you will come here, then you will come here, right? And that's the maximum time it's going to take. Because what might happen is you're searching for 15 and it's present at the root itself, right? In this case, it just takes the constant time. So the worst case time taken by any search is equal to height of the BST. If you're suppose searching for something like 19, then you will come here, then you will come here, then you will come here, then you will decide that's not present. So that's also maximized by or upper limited by height. You know, if you're searching for something like say 15.5, then you will come here, then you will come here, then you will come here, and then you will come here, and then you will decide that it's not present. So you're traversing exactly one extra than height, right? So its time complexity can be written as big O of h. Please note that I'm using big O, not theta, because h is an upper bound. It is at most h plus 1 comparisons. And it can be constant work also if it's present at the root only. So that's the time complexity for both recursive and iterative implementations, because the logic for both of them is same. They traverse across the height. So time complexity is big O of h. Now let's talk about auxiliary space. If you talk about recursive implementation, it requires auxiliary space for function call stack. And how many functions can be there in the function call stack? Let's see. Suppose you are searching for 16. This will begin, it will be there in the function call stack. It will call for the right, then it will call for the left, it will call for the left. So when you are here, all these functions are there in the function call stack. So auxiliary space required by the recursive implementation is big O of H. And how much auxiliary space is required by the iterative implementation? The iterative implementation does not require any auxiliary space. It works in constant auxiliary space because it's simply running a loop. So obviously, iterative implementation is better than recursive implementation because it does not require auxiliary space. Also, it does not involve extra function call overhead. Now, one last note about the search function. It is upper bounded by height. And if you have a binary search tree which is not balanced, it can become n. The height can become n. Suppose you are searching in this order. First you inserted 10, then you inserted 12, then you inserted 14, then you inserted 16. So height is actually equal to the number of nodes. So height can become n if your tree is skewed, if it is completely unbalanced. And in the best case, it can become log n when it is balanced. We are going to talk about self-balancing BSTs, which make sure that height never goes beyond order of log n. So in those cases, search becomes big O of log n. But when we talk about normal BST, height can be n. So we can say time complexity is big O of h only. We can't say it's big O of n or it's big O of log n because it can be anything. So big O of h is the best term to represent the search in a normal BST. But when you talk about self-balancing BSTs, which maintain their heights to be log n, we can call the search function as big O of log n.